Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen from the same book Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay. Find lambda m for black body radiation at part A T equal to 3 Kelvin, part B T equal to 300 Kelvin, and part C T equal to 3000 Kelvin. Okay, quite simple. Wein displacement law is applicable. Dear students, now we are going to its solution, but before starting its solution in a formal manner, we will introduce a snapshot. Okay, this snapshot has been chosen from the book University Physics by Young Friedman. Okay, according to this snapshot defines Wein displacement law for a black body. Okay, Wein displacement or I think Wein displacement law for a black body. Okay, lambda mt is equal to 2.90 into 10 raised to the power minus 3 meter dot Kelvin, where lambda m is the peak wavelength in spectral emittance curve. Okay, that is to say m standing for maximum. Okay, peak or maximum almost similar sense. Okay, and T is the absolute temperature of black body. Okay, remaining two are constants, that is meter and Kelvin. Okay, Wein displacement law, lambda mt equal to 2.90 into 10 raised to the power minus 3 meter, that is to say millimeter, into Kelvin. Okay, 2.9 millimeter Kelvin. Lambda m is the peak wavelength in spectral emittance curve, and T is the absolute temperature of black body. Okay, we will use this snapshot, and remaining nothing, our problem will be solved. So we can say that it is a short problem, but we have not distinguished between normal or a lengthy problem and short problem, so it is just a problem. Okay, whether lengthy or not. Okay, according to Wein displacement law for a black body, lambda mt is equal to 2.90 into 10 raised to the power minus 3 meter dot Kelvin. This implies that if we keep maximum wavelength lambda m, peak wavelength lambda m on one side, then temperature T will become in the denominator on other side of equality. That is to say, in other words, temperature will be divided. Okay, so lambda m, that is to say peak frequency, maximum frequency, frequency, not wavelength. Wavelength and frequency are reciprocal of each other. We are dealing with just wavelength lambda. Okay, maximum wavelength or peak wavelength. Okay, peak wavelength lambda into temperature T is equal to 2.90 into 10 raised to the power minus 3 meter dot Kelvin. Meter Kelvin. From here, if we keep lambda m maximum wavelength on one side, then temperature will be divided on other side. Okay, lambda m becomes equal to 2.90 into 10 raised to the power minus 3 meter Kelvin divided by T. Now we are just putting the values. Part A becomes lambda m equal to 2.90 into 10 raised to the power minus 3 meter dot Kelvin divided by 3K. In place of T, we have used its given value in part A, 3K. Here k will be cancelled with k, and our lambda m, that is peak wavelength, maximum wavelength, will become equal to 0.966 into 10 raised to the power minus 3 meter. Okay, we know that 10 raised to the power minus 3 is called milli. Okay, because when we divide a meter into equal 1000 parts, then each part is called millimeter. So it is our discretion whether we denote it by 10 raised to the power minus 3 or small m, that is milli. So it will become 0.966 millimeter. In part B, T in place of 3 Kelvin is given as 300 Kelvin. So dear students, we will see that its answer will also be of the similar nature, that is to say 966, but only power of tens will differ. Okay, so we will compare after solving this part. Okay, here peak wavelength or maximum wavelength lambda becomes equal to 2.90 into 10 raised to the power minus 3 meter Kelvin over 300 Kelvin. In place of 3 Kelvin as in part A, here is 300 Kelvin. Kelvin will be cancelled with Kelvin, and our maximum wavelength or peak wavelength will become equal to 0.00966 into 10 raised to the power minus 3 meter. We can write in like previous problem, we can write it as simply as 0.00966 millimeter. Oh, sorry, dear students, there is a minor mistake. Minor, not major. Okay, minor mistake is that there is a sign of equality here. Here there is a sign of equality. If I rectify this mistake during the lecture, then there is a probability that we may face difficulty, our system may be hanged. So I do not revert into the math type software, and then after rectifying the problem, I again cut paste from math type software and then copy paste it here. So it is sufficient when I have pointed out that there is a mistake of a sign of equality here. Okay, so dear students, 0.00966 millimeter. Yes, actually dear students, here in place of 0.000966, here we have shifted decimal 3 stages ahead. Okay, that is to say, in place of 0.00966 millimeter, we have written it as 9.66. When we write it in this way, then we will alternatively multiply it with 10 raised to the power minus 3, because we have shifted decimal 3 steps ahead. So it will become 9.66 into 10 raised to the power minus 3 millimeter. In other words, it will become 3 millimeter, 3 mm. It can once again be written as a milli, so millimeter, and we know that 2 milli, that is milli into milli, becomes equal to micro. Milli means 10 raised to the power minus 3, while micro means 10 raised to the power minus 6. So this will be equivalent to writing it as 9.66 into 10 raised to the power minus 6. Okay, this is 10 raised to the minus 3, and this milli is also 10 raised to the power minus 3. So these two will add and contribute as 10 raised to the power minus 6 meter, and we know that 10 raised to the power minus 6 is micro, which is usually denoted by mu symbol. So this has become equal to 9.66 micrometer. Okay, 10 raised to the power minus 6 is micro, while 10 raised to the power minus 9 is nano. We will see that in part C. We will have to deal with the nano. Okay, so our part B has been solved. Now we move to part C and we see how we come across nano. Okay, part C, maximum wavelength or peak wavelength lambda m becomes equal to 2.90 into 10 raised to the power minus 3 meter Kelvin divided by 3000 Kelvin. Kelvin will be cancelled with Kelvin, and our answer will become 9.66 into 10 raised to the power minus 4. Okay, into 10 raised to the power minus 3 meter. What we have done, dear students, what we have done, actually, dear students, we move to part A. Here in part A it was 0.966, 0.966, and here 0.966, 0.966 in place of 0.966 we have written 9.66. That is to say, we have shifted one step ahead, due to which in part A there was simply 3, while here is 3000. Okay, so dear students, actually in part B there was 300 and in part C there is 3000. It means difference between part B and part C is only of 10. 10. Okay, so in part B our answer has become this, while in part C our answer will be that here in place of 10 raised to the power minus 6 it will become 10 raised to the power minus 7, because 10 in place of 10 300 it is 3000. So dear student, 9.66 into 10 raised to the power minus 4 into 10 raised to the power minus 3, these two will add and make 10 raised to the power minus 7 meter. Dear students, now if we shift decimal 2 stages ahead, then this 10 raised to the power minus 7 will increase to 10 raised to the power minus 9. Okay, this is just a manipulation of mathematical step, quite simple, but sometimes a simple thing also confuses. Okay, so dear student, 10 raised to the power minus 7. Here we have on our own choice we have shifted decimal 2 stages ahead, due to which this power has also been increased in on negative side by 2, and hence it has become 10 raised to the power minus 9 meter. 966 into 10 raised to the power 9 meter, and we know that 10 raised to the power minus 3 is milli, 10 raised to the power minus 6 is micro, and 10 raised to the power minus 9 is nano. So our lambda m, that is maximum wavelength or peak wavelength, has become equal to 966 nanometer. And this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.